The night sky above the Texas coastline erupts in a column of fire so bright it turns darkness into day. A gleaming steel rocket, taller than a 20-story building, begins its violent dance with gravity. For a few breathtaking seconds, the machine hovers impossibly on a pillar of flame before settling gently onto its landing pad. This isn't science fiction. This is SpaceX, and this is how Elon Musk is rewriting the rules of space exploration. While traditional aerospace companies spend decades and billions on rockets that fly once and fall into the ocean, Musk's team catches theirs midair with giant mechanical arms. How does a company that didn't exist 20 years ago now dominate an industry that was once the exclusive domain of superpowers? When SpaceX was founded in 2002, the aerospace industry was stagnant. NASA's space shuttle program was aging and expensive. Each launch cost around $450 million. Russia's Soyuz spacecraft, while reliable, was technology from the 1960s. China was just beginning its space ambitions. Private companies, they built components, sure, but the idea of a startup building orbital rockets was considered absurd. The industry operated on cost-plus contracts where companies were paid their expenses plus a profit margin. There was no incentive to innovate or reduce costs. Rockets were disposable, like throwing away a $750 million airplane after one flight. The mathematics were brutal. Getting 1 kilogram to orbit cost around $20,000. Launching a satellite could easily exceed $100 million. This made space access the privilege of governments and the wealthiest corporations. Meanwhile, the dream of humanity becoming a spacefaring civilization remained exactly that, a dream. Musk saw this differently. He asked a question that seemed naive to industry veterans, but was actually revolutionary. Why does it cost so much? The materials in a rocket, he calculated, were only about 2% of the launch price. The answer wasn't in the raw materials, but in how the entire industry operated. And the first challenge was finding the right people and the right approach. Traditional aerospace companies had layers of management, endless reviews, and risk-averse cultures shaped by government oversight and shareholder expectations. SpaceX needed to move fast and take risks. Musk recruited hungry young engineers, many fresh from universities, who didn't know what was supposedly impossible. He hired experienced aerospace veterans who were frustrated by the slow pace of traditional companies. But talent alone wasn't enough. The company needed a different structure. Instead of outsourcing components to hundreds of subcontractors, SpaceX decided to manufacture almost everything in-house. This was considered madness. Boeing had 30,000 suppliers. SpaceX would make its own engines, avionics, structures, even the bolts and rivets. This vertical integration gave them control over quality, costs, and most importantly, iteration speed. When something didn't work, they could redesign it immediately rather than waiting months for a subcontractor. The company established its headquarters and manufacturing facility in Hawthorne, California, in a building that once made airplane fuselages. The factory floor became a hive of constant activity, where engineers and technicians worked side by side. The technology decisions SpaceX made were equally unconventional. The aerospace industry loved exotic materials and complex designs. SpaceX went the opposite direction. Their Falcon 1 rocket, the company's first attempt, used a relatively simple design with a single engine burning kerosene and liquid oxygen. Industry standards demanded extensive documentation, multiple review boards, and testing cycles that could take years. SpaceX compressed this timeline dramatically. They embraced a philosophy that would become their signature: test, fail, learn, repeat, fast. The Merlin engine that powers Falcon rockets went through rapid iterations. Instead of spending years perfecting a design on paper, they built engines, fired them, studied the failures, and rebuilt them. This approach horrified traditional aerospace engineers who were taught that failure was unacceptable. But Musk understood something crucial. Failure during testing is information. It tells you exactly what doesn't work. 3 times Falcon 1 failed to reach orbit. Each failure nearly bankrupted the company. The 4th launch, in September 2008, succeeded. SpaceX became the first private company to put a liquid-fueled rocket into orbit, but the real challenge was still ahead. The true revolution was reusability. Imagine if every airplane could only fly once. Air travel would cost millions per passenger. That's essentially how rockets worked. SpaceX needed to solve a problem that had stumped the industry for decades. How do you bring a rocket back and land it safely? The physics are punishing. A Falcon 9 first stage is 15 stories tall, weighs 20 tons empty, and after separating from the second stage, it's traveling at over 5,000 miles per hour at the edge of space. It needs to flip around, reignite its engines, survive re-entry temperatures that can exceed 3,000 degrees, and land precisely on a platform smaller than a football football field. Engineers developed sophisticated software that could calculate landing trajectories in real time, adjusting for wind, weight changes as fuel burned, and atmospheric conditions. They created grid fins, massive titanium plates that deploy to steer the rocket through the atmosphere. They designed landing legs that could absorb the impact of a 15-story building touching down. The first attempts were spectacular failures. Rockets crashed into the ocean. One famously hit the drone ship landing platform and exploded. Musk posted the videos online, turning failures into viral content and public learning moments. Finally, in December 2015, a Falcon 9 first stage landed successfully at Cape Canaveral. The sonic booms rattled windows for miles. The impossible had become real. Making reusability actually economical required solving countless engineering challenges. A rocket that lands is subjected to enormous stresses. Salt water from ocean recovery corrodes components. Heat from re-entry damages surfaces. Every part needs inspection and potential refurbishment. SpaceX attacked this systematically. They developed heat shields that could withstand multiple re-entries. They designed engines that could be fired dozens of times with minimal maintenance. They created inspection protocols using advanced sensors and AI to detect microscopic cracks or wear. The turnaround time between flights dropped from months to weeks to days. Some boosters have now flown over 20 times. The company's Starship program takes reusability even further. The entire rocket, both stages, is designed to be fully reusable. And instead of landing on legs, they're developing a system where the launch tower catches the returning booster with giant mechanical arms. When they successfully demonstrated this catch for the first time, jaws dropped worldwide. Testing at SpaceX doesn't follow traditional aerospace timelines. Where NASA might spend a decade developing a new rocket engine, SpaceX builds, tests, and iterates in months. Their facility in McGregor, Texas serves as a massive test site where engines fire constantly. They don't just test until something works, they test until it breaks, then test again to understand the margins. The company embraces rapid iterative development. Build a prototype quickly, test it to destruction, learn from the failure, incorporate improvements, and repeat. Starship prototypes famously exploded during early testing. Each explosion provided data worth millions of dollars in analysis. Where other companies would have hidden these failures, SpaceX often live-streamed them, turning engineering development into public spectacle. This approach extends to software too. The flight computers and control systems running SpaceX rockets are constantly updated. They can push software changes to rockets on the pad just like updating a smartphone app. The impact of SpaceX's innovations ripples far beyond cheaper satellite launches. They've fundamentally shifted what's economically possible in space. Before SpaceX, launching a satellite to low Earth orbit cost well over $20,000 per kilogram. Falcon 9 reduced this to around $3,000. Starship aims for under $100 per kilogram. This isn't just incremental improvement, it's orders of magnitude change that enables entirely new possibilities. Suddenly, massive satellite constellations become viable. SpaceX's own Starlink network, with over 5,000 satellites providing global internet coverage, would have been economically impossible without cheap, frequent launches. Scientific missions that were shelved as too expensive become feasible. NASA selected Starship as the lunar lander for their Artemis program to return humans to the moon. The ability to launch hundreds of tons to orbit per flight at low cost changes the fundamental economics of space exploration. Mars missions, once century-away dreams, enter the realm of current decade planning. Are you amazed by how one company changed an entire industry by simply asking why things had to be so expensive? SpaceX didn't just build better rockets, they built them differently, challenging every assumption about how aerospace engineering had to work. The shiny steel rockets standing in South Texas represent more than engineering achievement. They represent a different way of thinking about exploration and humanity's future beyond Earth. Follow for more stories about the people and companies refusing to accept the impossible.